Welcome to the Deep Dive. Today, we're embarking on a journey into something really foundational, something that reshaped how we process truly enormous amounts of data. Imagine yourself working at a company like Google, maybe back in the early 2000s. You've got just mountains of information, every single web page they ever crawled, right? Every search query typed, every web server log entry. We're not just talking gigabytes or even terabytes here. We're talking petabytes and beyond. I mean, quantities of data that just dwarfs anything a single computer could ever hope to handle. And your job is to make sense of all of it, quickly, reliably. You need this to power search engines, to analyze trends, build new products. That sounds like a monumental task, doesn't it?
It absolutely is. Yeah, for a long time, dealing with data at that kind of scale meant wrestling with incredibly complex programming. You weren't just writing the logic for what you wanted to compute, you were also managing, countless individual machines, constantly battling against inevitable hardware failures, network glitches, just like trying to orchestrate everything.
Sounds exhausting.
It was very much a specialist's game, full of intricate, bespoke solutions, things that often didn't translate well from one problem to the next. It felt like every new large-scale problem meant building a custom, very fragile skyscraper from scratch.
But then, something came along that fundamentally changed the game. It introduced a remarkably simple programming model, one that made these colossal computations approachable, even for programmers who didn't have a deep background in distributed systems. We're talking about MapReduce, that ingenious programming model and its implementation born out of Google, which dramatically simplified data processing on large clusters.
Exactly. And our mission today is to unpack this powerful concept for you, especially if you're maybe new to the world of distributed systems. We'll start by exploring the immense problem it set out to solve, why traditional computing models were failing spectacularly at this scale, and the sheer headache it caused engineers.
Right, what was so broken?
Then we'll dive into the elegant simplicity of its core idea, these map and reduce functions. We'll show you just how little code you actually had to write, which was kind of the magic part. After that, we'll pull back the curtain and show you how it actually makes all that distributed magic happen behind the scenes. From splitting data across machines to intelligently handling failures.
The nuts and bolts?
Yeah, the nuts and bolts. And finally, we'll look at some fascinating real-world examples from Google itself and the incredible performance gains it delivered. By the end of this deep dive, you'll leave with, I hope, a clear understanding of a critical piece of modern computing history and the profound ideas that underpin so much of today's big data infrastructure.
Okay, so let's set the scene. Imagine you're at Google, early 2000s, or really any fast-growing tech company dealing with this explosion of digital information. Before MapReduce, what kind of massive data problems were they grappling with? What were they trying to achieve that was just so difficult with the tools they had back then?
Well, companies like Google were, and still are, fundamentally in the business of understanding the world's information, right? And that meant constantly implementing what they called special purpose computations on large amounts of raw data. Let's paint a clearer picture of what large amounts of raw data really meant. I mean, just think about all the documents Google had crawled from the web.
The whole internet, basically.
Pretty much. Every single web page they could find. This wasn't just gigabytes. It was, and continues to be, this ever-growing vast ocean of text and links. Petabytes of information. Just try to imagine having to read every single word on every single web page on the internet. That's one type of raw data.
Okay, that's huge. And what else? I imagine they were tracking user interactions too, clicks and searches.
Precisely. Then you have the logs of web page requests. Every time someone searches, clicks a result, visits a Google service, types a query, these logs represent billions, literally billions, of discrete events every day. Each one a tiny piece of information, but when you aggregate them, it quickly becomes overwhelmingly massive. We're talking about individual log files that could be tens or hundreds of gigabytes, and collections of these spanning thousands of machines. It just piles up incredibly fast.
And they weren't just storing this data passively, right? They needed to extract useful stuff from it, what they call derived data. Can you give some concrete examples of what they were trying to compute?
Absolutely. One of the most fundamental derived data sets they needed was the inverted index. If you use a search engine, this is the absolute backbone. Think about how search works. You type a word, deep dive perhaps, and it instantly finds relevant documents. An inverted index is basically a giant lookup table. It goes from a word like deep dive to a list of all the documents that contain that word, and maybe where in the document it appears. Before MapReduce, just building and maintaining such an index for the entire web, which is constantly changing, was a truly monumental undertaking.
I can only imagine. What other insights were they trying to pull out of this data deluge?
Another critical piece was understanding the representation of the graph structure of web documents, which basically means figuring out how web pages link to each other.
Ah, like PageRank.
Exactly. That web graph is vital for algorithms like PageRank, which helps determine the authority and relevance of pages. Beyond that, they wanted things like summaries of crawled pages per host. How many pages did we crawl from example.com? This helps understand website health, find spam, track changes, and of course identifying the most frequent queries in a given day. That's vital for understanding user behavior, spotting trends, improving search results, placing ads, all sorts of things. All these computations, while conceptually maybe simple on a small scale, became incredibly challenging at the scale Google operated.
So the core computations themselves, like counting words or finding links, they weren't rocket science in theory, but the sheer scale made them a nightmare in practice. It sounds like the typical approach, just running things on one big, powerful computer, just wasn't going to cut it anymore.
Not even close, exactly. The input data was usually large, many terabytes, which back then was just an astronomical amount, maybe equivalent to thousands of the hard drives you'd have at home. And to process this and get results in a reasonable amount of time, meaning minutes or hours, definitely not days or weeks, these computations had to be distributed.
Spread out.
Spread out. You couldn't just throw one supercomputer at it. You needed to spread the work across hundreds or thousands of machines. And this is where the messy details problem really came in. For a programmer, this meant immense complexity. They had to manually figure out how to, first, parallelize the computation. How do you break a single huge problem into thousands of tiny pieces that can run at the same time on different machines? It's not trivial.
Yeah.
Second, distribute the data efficiently. How do you get the right data to the right machine without choking the network? Imagine trying to manually coordinate moving petabytes of data around thousands of computers. And third, handle machine failures gracefully. This is a big one. In a cluster of thousands of cheap commodity machines, the simple truth is machines will fail. Hard drives crash, network cards glitch, memory goes bad.
It's just statistics at that point.
Exactly. If your computation runs for hours, it's a certainty that dozens, maybe hundreds of machines will drop out. So dealing with these failures, detecting them, restarting lost work, ensuring data integrity, making sure the whole thing didn't just grind to a halt was incredibly difficult.
And what was the end result of all that complexity for the poor programmers trying to build these systems? What's been frustrating?
Oh, it led to large amounts of complex code. Imagine trying to write the simple logic for counting words, but then having to weave in thousands of lines of code just for network communication, error handling, retry loops, load balancing across hundreds of machines. Yeah. The actual problem they were trying to solve, the simple computation, got completely buried under layers and layers of this intricate, fragile infrastructure code. This complex code obscured the original simple computation. It was a huge barrier, even for expert programmers. For you, the listener, you might have felt the pain of trying to scale even a simple app across just a few computers, right? Getting bogged down in networking, error handling.
Oh, yeah.
Now imagine that, but multiply it by thousands of machines, data flying everywhere, machines constantly blinking in and out of existence. That's the persistent headache MapReduce was designed to cure. It was about making that pain just disappear.
And this is where the genius of MapReduce came in. It was a direct reaction to that complexity, like saying, enough of this, there have to be a better way.
Precisely. The goal was to design a new abstraction, something that allowed programmers to express those simple computations like counting words or building an index, while completely hiding all those messy details we just talked about.
Sweeping it under the rug, but in a good way.
In a very good way. The idea was that the MapReduce library itself would become the workhorse. It would handle all the distributed systems challenges automatically. It takes care of the parallelization, figuring out how to break work into pieces and run them simultaneously. It handles fault tolerance, so if a machine dies, the computation doesn't crash. It recovers, picks up where it left off, maybe reruns some parts. It manages data distribution, moving data around intelligently without you writing any network code. And it takes care of load balancing, making sure work is spread evenly, maximizing efficiency. So it's like providing this super simplified interface to a massive complex machine, turning that nightmare into something manageable. And where did the core idea, this powerful abstraction, actually come from? The inspiration, interestingly, was the map and reduce primitives present in Lisp and many other functional languages. These are powerful, high-level operations often used for list processing. The Google engineers realized that most of their large-scale computations involved a very specific two-step pattern that mirrored these functional concepts. First, applying a map operation to each logical record in their input data. This map step transforms each piece of data into a set of intermediate key-value pairs. Then second, applying a reduce operation, which takes all the values associated with the same intermediate key and combines them somehow. This insight that so many seemingly different problems could be broken down into these two simple functional steps was the breakthrough. It allowed them to build a library that could automatically parallelize these computations and use re-execution, just retrying failed tasks, as the primary way to handle failures automatically. It's an incredibly elegant simplification.
Okay, let's unpack this then. We've heard map and reduce mentioned as these functional concepts, but what exactly is this idea in the context of MapReduce? How does it turn these complex, large-scale problems into manageable two-step operations that a giant cluster can process?
At its most basic level, the MapReduce model takes a set of input key-value pairs. You can sort of imagine a massive spreadsheet where each row is a key-value pair. And after processing, it produces a new set of output key-value pairs. The real elegance is that you, the programmer, you don't need to worry about managing machines or networks or failures. Your entire job is just to provide two simple functions, map and reduce. That's it. The whole magic of distributed computing is abstracted away behind those two functions.
Two functions. Okay, let's dive into the map function first. What's its role? What does it actually do?
The map function is the first piece of code you write. Its job is pretty specific. It takes a single input key-value pair. Think of this input pair as one record from your massive data set. Maybe it's a line from a web server log, or the contents of a single web page, perhaps identified by its URL key. For each input pair it processes, your map function then produces a set of intermediate key-value pairs. It might produce 0 pairs, 1 pair, or many pairs.
Okay.
For example, if your input is a document, your map function might read through it, and for every single word it finds, output an intermediate pair, like word 1. It's basically extracting data and assigning a temporary key to it, getting it ready for the next stage.
And the library, the MapReduce framework, does something crucial with all those intermediate pairs, right? They don't just sit there on the machine that created them.
Yeah, precisely. This is where the MapReduce library takes over automatically. It collects all those intermediate key-value pairs that all your different map functions have produced, potentially across thousands of machines in the cluster. This is part of the shuffle stage we'll touch on more later. Then, crucially, it automatically groups together all intermediate values that are associated with the same intermediate key. So if many different map functions run on many different machines, each emitted the v1, the library gathers all those individual ones and presents them as a single list associated with the key v. This consolidated list is then passed on to the reduce function. You don't manage any of this complex grouping or data movement. The library handles it all for you.
Okay, so map extracts and tags, the library groups. And then comes the reduce function, the second piece of code you write. What does it do with that grouped data?
The reduce function, also written by you, the user, receives one intermediate key, like the word the, and then it gets all the values that the map functions produce for that specific key. So for the word the, it might receive a list like 111 if the word appeared 4 times across all the documents processed by the map tasks. Its core job is to merge together these values to form a possibly smaller set of values. Typically and most commonly, it produces just 0 or 1 output value per key it processes. So for the list 1111, it would merge them probably by summing to produce a single count, like 4.
And there's an important detail about how it gets that list of values, especially if it's huge.
Yes, a really important design detail, crucial for handling truly massive data. The list of values is provided to the reduce function via an iterator. This is critical because it means the library can handle lists of values that are far too large to fit entirely in memory, maybe billions of values, for a single popular key. The reduce function can process them piece by piece using this iterator without crashing your machine. It can even spill intermediate results to disk if needed. It's built for scale.
That iterator concept for potentially enormous value lists is subtle but clearly powerful. Okay, let's make this really concrete with a classic example that always seems to drive home how simple the user's part is. Counting word occurrences in a huge collection of documents.
Yeah, it's a perfect illustration. Imagine your input to MapReduce is a collection of documents. Each input pair could be document ID, document contents. Let's say one document, doc1, contains the text, the quick brown fox. So for the map function, for a word count, you'd write something simple. Your map function gets Doc1, the quick brown fox thee. It goes through the document contents word by word. For each word it finds, it emit intermediate word 1. So from that example sentence, your map function would emit the 1, quick 1, brown 1, fox 1, the 1. See? For every occurrence, it just emits the word as the key and a simple count of 1 as the value. Very straightforward, per word operation.
Right, just breaking it down. And then the MapReduce library orchestrates collecting all those word 1 pairs from potentially millions of documents processed across thousands of map tasks. How does the reduce function then bring it all together for the final count?
Exactly. The library, remember, collects and groups all these intermediate pairs across all documents, no matter which map task produced them. So for the word the, it eventually gathers all the values associated with the from every single map task that encountered it. The reduce function would then receive something like the 1111, where that list of ones could be, tens of millions long for a common word. Your reduce function then simply iterates through that list, using the iterator, of course, and sums them up. If it saw the 1, 1 from our tiny example, it would calculate 1 plus 1 equals 2, and then it would emit the as the final output for that word. That pseudocode really highlights how deceptively simple the user's part is, right? While the library handles all the incredibly complex heavy lifting of parallelism, data distribution, fault tolerance, everything else, you just define the transformation for one item and the system scales it to a trillion.
That is incredibly elegant. You just tell it what to do with individual pieces and how to combine the results, and it figures out the whole distributed mess on its own. It sounds like a really powerful paradigm. To show you just how versatile this model is, maybe you walk us through a few more quick examples from the original paper, just to highlight different ways you can use map and reduce.
Sure. First, distributed grep. This is basically like searching for a specific pattern, say a particular keyword or phrase, across a massive number of text files, maybe petabytes of logs. You, the user, would just write a map function that looks at each line of input it gets. If that line matches your pattern, your map function just emits the entire line itself as an intermediate value. Maybe the key doesn't even matter much here.
So it filters.
Exactly. Map
Good.
filters the data. The reduce function in this case is super simple. It's what's called an identity function. It just copies whatever intermediate value the matching line it receives directly to the final output file. So map filters, reduce collects. Simple as that.
Okay, next, count of URL access frequency. This sounds like something Google would do constantly, right? To figure out which web pages or services are most popular.
Indeed. For this, your map function would process logs of web page requests. Each log entry might contain a URL that was accessed. So for every URL it sees, your map function outputs an intermediate pair like URL 1, just like the word count, but with URLs. If the same URL appears many times, it emits URL 1 for each time. Then the reduce function receives a URL and that list of all the ones associated with it, its job. Just sum them up to get the total count for that URL. The final output would be URL total X count. Simple, efficient, and instantly useful for analytics.
Makes sense. And finally, a core search engine component, the inverted index. This one seems maybe a bit more complex than just counting or filtering, but it still fits the model.
It absolutely does. The map function here would parse each document. For every word it finds in a document, it emits a word document ID pair. Document ID is just a unique identifier for that document. So if deep appears in document 123, it emits deep doc123. The library then groups all these pairs by word. So your reduce function would receive a word, let's say deep, and then a list of all the document ID where that word appeared. Deep, doc123, doc456, doc789.
I see.
The reduce function then collects all those document IDs, maybe sorts them numerically or alphabetically for efficiency, and emits a final pair, like word list of sorted document IDs. The entire collection of these output pairs for all words forms your simple inverted index. It lets a search engine quickly find all documents containing a given word. Fundamental to search. The versatility really just comes from how you define those two relatively small functions, map and reduce.
Okay, so we've got this beautiful, simple programming model. User provides two functions, map and reduce. Done. But the real magic, right, the part that makes it so powerful and truly revolutionary is the associated implementation. This is where it gets really interesting. How does this elegant idea actually happen on thousands of machines? How does it handle all the data movement, the inevitable failures we know are coming? Let's look under the hood.
That's right. And the implementation we're talking about, the original one designed by Google, it was specifically tailored for their computing environment at the time, which was these massive clusters of commodity PCs. This is important. They weren't using super expensive bespoke hardware. They used standard, off-the-shelf computers, cheap and readily available. The challenge was making thousands of these relatively cheap machines work together reliably, like a single, powerful supercomputer.
What did those machines typically look like back then? And what were the big implications of using so many of them?
A typical machine might have, say, dual processor by 86 CPUs, maybe 2 to 4 gigabytes of memory, which sounds tiny now for big data, but was decent then, and connect to the network with 100 megabit or maybe 1 gigabit Ethernet. The key characteristic, though, was the sheer scale. Hundreds or thousands of machines. This scale is crucial because it means machine failures are common. Like we said, not a theoretical possibility, an everyday reality.
Right.
If you have 1,000 machines running for hours, some will fail. Hardware glitches, software bugs, network issues, it happens. For storage, they used inexpensive IDE disks, just directly attached to individual machines, no fancy storage arrays. And the data stored on these disks was managed by Google File System, GFS. GFS uses replication, storing multiple copies of the data to provide availability and reliability, even on top of this unreliable commodity hardware. Think of GFS as this massive, reliable library for all the cluster's data, accessible from any machine.
Okay, so that's the environment. Now let's walk through the actual execution flow. You described it as a carefully choreographed dance between a central master and many workers. Where does it all begin when I, as a user, want to run a MapReduce job?
It starts with your user program. Step 1, input splitting and program launch. When you make that call to the MapReduce function in your code, the library first takes your massive input files, which might be spread across many machines in GFS, and automatically splits them into M pieces, or splits. These pieces are typically, say, 16 to 64 megabytes each. Why split them? So the work can be parallelized across many machines. Then the MapReduce library launches many copies of your MapReduce program across the cluster. These are all the potential worker processes just sitting there ready for instruction.
Okay, so a bunch of identical programs launch. How do they know what to do? Who's in charge?
That's step 2, master and worker assignment. One of those program copies gets designated as special. It becomes the master. All the other copies become workers. The master's job is to orchestrate everything. It keeps track of the state of every single map task and every single reduce task. It continuously picks idle workers and assigns them tasks. There are M map tasks in total, 1 for each input split we created, and R reduce tasks. You, the user, usually specify R, the number of reduced tasks you want, maybe a few hundred, maybe 1,000, depending on how you want your output split up.
Got it. So the master assigns a map task to a worker. Then what happens?
That's step 3, map task execution. A worker assigned a map task is told which specific input split it needs to process. It reads that assigned input split from GFS, often directly from its own local disk, thanks to GFS's replication strategy, which we'll talk more about. It then parses the key value pairs out of that data one by one. For each input pair, it feeds it to your user-defined map function. The intermediate key value pairs that your map function produces, like the word 1 for word count, aren't immediately sent anywhere. Instead, they're initially just buffered in the worker's memory, a temporary holding area.
Buffered in memory. But those eventually need to go somewhere more permanent, right? What's step 4?
Step 4, writing intermediate data. Periodically, those buffered intermediate pairs in the worker's memory get written out to the worker's local disk. This is a critical detail. They stay on the local machine for now, do not send over the network yet. Why? It reduces network traffic initially and allows some local processing, like combining before the big data shuffle. But as they're written, they're also carefully partitioned. They get divided into R regions, 1 for each reduced task. So if you specified 100 reduced tasks, a single map worker will create 100 small files on its local disk. Each file contains intermediate key value pairs destined for a specific reduced task. For example, all keys starting with A go to reducer 1, B to reducer 2, etc., based on a partitioning function. Once these files are written locally, the map worker tells the master the locations of these files. Basically, here's where the data for reducer 1 is on my disk, here's for reducer 2. The master acts as the central directory for all this intermediate data.
Okay, so the map tasks are creating these partition files locally. But eventually, the reduced tasks need to get all the data for their specific keys, no matter which map worker produced it. This sounds like the shuffle phase you mentioned, where all that data gets moved around the network.
It is, yeah. And this is where the real magic of distributed data movement happens, in step 5, the shuffle phase. When a reduce worker is assigned its task, say reducer 5, the master tells it the locations of all the relevant intermediate files, the files created for reducer 5, which are scattered across the various map workers' local disks. The reduce worker then uses remote procedure calls, RPCs basically, network messages to talk to other computers to pull this data from those map workers' local disks. It gathers all the pieces destined for it.
So it actively fetches the data it needs.
Exactly. Once it has all the intermediate data for the keys, it's responsible for example, all the values for the word apple from every single map task. It sorts this data by the intermediate key. This sorting step is crucial because it groups all occurrences of the same key together, making it easy for your reduce function to process them all at once. If this aggregated data is too large to fit in memory, which happens often, it uses an external sort. It sorts chunks on disk and then merges them efficiently. This shuffle phase involving all this network I/O and sorting is often the most time-consuming part of a MapReduce job.
Right, moving all that data around takes time. So after all that complex data collection and sorting, the reduce worker is finally ready to do its actual job, the one we defined. That brings us to step 6.
Step 6. Reduce task execution. The reduce worker now iterates over its sorted intermediate data. For each unique intermediate key it encounters, say the word the, it passes that key and the corresponding list, iterator, of all intermediate values, for example 1111, to your user-defined reduce function. The output of your reduce function, like the for, is then appended to a final output file. This output file is specific to that reduce partition, and importantly, it's written to the global file system, GFS. Each reduce task writes its own separate output file to GFS, which ensures the final result is durable and available even if the reducer worker fails later.
So final output goes to the reliable global storage. And then when is the whole MapReduce operation considered finished? How does the user know the job is done and the results are ready?
That's step 7, completion. Once all mmap tasks and all reduce tasks have successfully completed and their final outputs are safely stored in GFS, the master sends a signal back to your original user program. The MapReduce call returns, and at this point, the final output of your massive computation is available to you in those R output files, accessible through GFS. Often, these R files might become the input for another MapReduce job, which is a powerful way to chain together complex, multi-stage computations. Or they can just be used by other distributed applications.
It really sounds like the master's doing a lot more than just assigning tasks. It's truly the central brain, keeping everything synchronized, tracking everything.
It absolutely is. The master's role is much more than just scheduling. It's the central coordinator. It's the conduit that propagates the locations of all those intermediate files from the map tasks to the correct reduce tasks. It continuously keeps track of the state of every single task. Is it idle, in progress, completed, and which worker machine is assigned to it? It also constantly monitors worker health through those pings. This constant monitoring and communication ensures everything runs smoothly and, critically, allows for that robust error handling we need to talk about next. Without that central brain, the whole thing would just fall apart into chaos pretty quickly.
Okay, so we've outlined how MapReduce distributes the work using this master worker model and the MapReduce functions. But what does this all mean for dealing with the inevitable chaos of a large distributed system? Like you said, when you have hundreds or thousands of machines, something will go wrong. A disk fails, a network cable gets unplugged, a machine just becomes unresponsive. This is where MapReduce truly shines, right? Its fault tolerance is baked in, a cornerstone of its design.
Absolutely. Graceful handling of machine failures is fundamental. They built it assuming failures would happen, not if they might happen. The system just has to be resilient. The master acts like this diligent supervisor. It constantly pings, sending small network messages to every worker in the cluster. If a worker doesn't respond within a certain time, maybe 10 seconds, it's configurable. The master marks it as failed. And this is where the different handling for map versus reduce tasks comes in, and it's a really crucial detail for correctness and efficiency.
Okay, tell us about that distinction. What happens if a map worker fails? Maybe in the middle of its task or even after it thought it was done.
Right. If a worker that was performing map tasks fails, any map tasks that the failed worker had completed are immediately reset by the master back to an idle state. This makes them eligible for rescheduling on other healthy workers. Why? This is vital, because the output of completed map tasks, remember, is stored on the local disk of the failed machine.
So if the machine is dead, that data is gone.
Exactly. If that machine is dead or unreachable, its local disk is inaccessible, and that intermediate data is effectively lost. So that specific slice of map work has to be redone by a different worker. And of course, any map tasks that were in progress on the failed worker are also reset and rescheduled.
But reduced tasks are handled differently if their worker fails.
Yes, and this is a key distinction. Completed reduced tasks do not need to be re-executed if their worker fails. Why the difference? Because their final output is stored in the global file system, like GFS. That global file system is designed for reliability. Its data is replicated across multiple machines. So even if the worker that finished the reduced task dies, the output it wrote is safe and accessible from anywhere else in the cluster. Of course, just like with Map, any reduced tasks that were in progress on the failed worker are also reset to idle and immediately rescheduled on a new, healthy worker. This distinction between local storage for intermediate map results and global storage for final reduced results is fundamental to MapReduce's fault tolerance strategy.
That sounds incredibly robust. Do you have a real-world example of this resilience in action? It's one thing to talk about it theoretically, but seeing it endure massive failures must have been impressive.
Absolutely. The original paper gives this incredible example. During one large MapReduce operation at Google, network maintenance caused groups of 80 machines at a time to become unreachable for several minutes. Think about that. 80 machines just vanishing from the network simultaneously, not just one or two.
Wow.
But MapReduce, instead of just crashing and forcing someone to manually restart the entire hours-long computation, simply re-executed the work that was previously handled by those unreachable workers. It continued to make forward progress, eventually completing the MapReduce operation. That level of automated recovery with no human intervention needed for such a massive failure event is really a hallmark of robust distributed systems and a testament to MapReduce's assumed failure design.
Okay, worker failure is handled incredibly well. What about the master itself failing? That sounds like it could be catastrophic since it's coordinating everything. Is that also handled automatically?
That's a good question. While it's less common, since there's only one master compared to thousands of workers, it technically remained a single point of failure in their original implementation. The paper notes that the master could theoretically write periodic checkpoints of its internal state, saving its progress regularly. If the master task then died, a new copy could potentially be started from the last saved checkpoint. However, in their initial implementation, maybe because master failure was deemed unlikely enough compared to worker failure, the computation would actually just abort if the master failed. The client program that started the job could then detect this abort condition and just retry the entire MapReduce operation if desired. So not fully automatic recovery for for workers, but the overwhelming focus was on worker failures, which are far more frequent and thus more critical to handle gracefully without stopping everything.
Okay, so even with all this potential re-execution and rescheduling happening because of failures, does the final output always make sense? Like, do you get exactly the same result you would have gotten if nothing ever failed and it just ran perfectly smoothly?
That's a great question, and it gets to this idea of deterministic semantics. For most user-defined map and reduce functions, which are typically designed to be deterministic, meaning they always produce the same output for the same input every single time, with no side effects, the distributed MapReduce implementation guarantees that it produces exactly the same output as if it had been run sequentially on a single reliable machine without any failures.
That's a powerful guarantee for programmers. How do they achieve that?
It relies on atomic commits of task outputs. Basically, each map task writes its intermediate output to its local disk. Each reduced task writes its final output to private temporary files in the global file system, GFS. Only when a task fully completes successfully is its temporary output file atomically renamed to its final visible name. Atomic rename is an operation provided by the file system that's guaranteed to happen instantaneously and completely, or not at all. So, if the same reduced task happens to be executed multiple times due to failures or backup tasks, they all write to temporary files. But only one of them will succeed in atomically renaming its temporary file to the final output file name. The others will fail to rename. This underlying file system guarantee ensures that only one consistent version of the output wins, preventing corrupted or inconsistent results. It makes it incredibly easy for programmers to reason about their program's behavior, even in this potentially chaotic, fault-ridden environment.
That's clever. Okay, so beyond just surviving failures, MapReduce is also incredibly smart about how it uses resources, right? Especially network bandwidth, which you mentioned can be surprisingly scarce and expensive in these large clusters. How does it optimize for that?
This is where the locality optimization comes in, and it truly is genius. Remember we said the input data is typically stored on the local disks of the machines in the cluster, managed by GFS, and GFS divides files into blocks, say 64 millibits, and stores multiple copies, or replicas, typically 3 copies, on different machines for reliability.
Right.
The MapReduce master leverages this GFS location information. When it needs to schedule a map task for a specific input split, a 64 millibit block for instance, it looks at which machines hold a replica of that data block. It then tries to schedule the map task on one of those machines. It's like asking a librarian to fetch a book, but if the book is already sitting on your desk, they just tell you, it's right there, pick it up.
So the data doesn't have to travel far, potentially not across the network at all.
Exactly, that's the huge payoff. When running large MapReduce operations on a significant fraction of the workers in a cluster, most input data is read locally and consumes no network bandwidth. Instead of pulling gigabytes or terabytes of input data over the network from some distant machine, the map task often reads it directly from its own local disk. This is a massive efficiency gain. It dramatically reduces network congestion, frees up that precious bandwidth for the crucial shuffle phase later on, where data has to move, and significantly speeds up the overall computation. It's an elegant solution that exploits the underlying storage system's design.
That is a fantastic optimization. But what about machines that aren't necessarily failed but are just slow, lagging behind for some reason? You mentioned stragglers earlier. That sounds like it could still mess up the timing.
Ah, yes, the stragglers. Even with perfect fault tolerance and locality, some machines can just be unusually slow. It happens. Could be due to various reasons. Maybe a bad disk experiencing frequent errors, leading to incredibly slow read performance. Maybe competition for CPU, memory, or network from other tasks running on the same machine. Or even, as the paper amusingly notes, a bug in the machine's setup code that accidentally caused processor caches to be disabled on a few machines, making computations on them slow down by a factor of over 100.
Wow, 100 times slower.
Yeah. These stragglers, even if there are only a few of them, can disproportionately lengthen the total time it takes for a MapReduce operation to finish, especially if they're holding up the very last few remaining tasks. Imagine a relay race where one runner is just agonizingly slow. Everyone else has finished their leg, but the whole team is stuck waiting on that one person.
Right, the whole job waits for the slowest task. So how does MapReduce deal with these stragglers without just waiting, potentially forever?
They have this general mechanism called backup tasks, or as I like to call it, the straggler killer. Here's how it works. When a MapReduce operation is nearing completion, say 99% of the map tasks are done, and maybe 95% of the reduced tasks are done, but a handful are still running, the master proactively schedules backup executions for those few remaining in-progress tasks. These are essentially duplicate tasks, running the same work but on different, hopefully faster idle machines. The original task and the backup task run in parallel. The overall task, e.g. map task, #123, is then marked as complete as soon as either the primary execution or the backup execution finishes.
Ah, so you take the winner. You don't have to wait for the slow one.
Exactly. You don't have to wait for the absolute slowest machine. You just wait for the first one, primary or backup, to cross the finish line. It's like having a second runner start the last leg of the relay if the first one seems to be struggling, and you just take the time of whichever one finishes first.
That seems like such a simple idea, but I bet it has a dramatic impact on the overall job completion time, especially for those really long jobs.
It absolutely does. The paper states this mechanism significantly reduces the time to complete large MapReduce operations. For instance, they measured a specific sorting program and found its completion time increased by a whopping 44% when backup tasks were disabled.
Nearly half again as long.
Yeah, just because of a few slow machines dragging things out. The beauty is that this backup task mechanism typically increases the overall computational resources used by only a few percent. You run a few extra tasks, but only near the very end. It's a small price to pay for such a significant speed up and predictable job completion time. It's a really pragmatic approach to dealing with the messy reality of performance variability in large clusters.
That's very clever. Are there any other nifty refinements or optimizations that make MapReduce even more powerful or efficient for developers?
Yes, a couple of others are definitely worth noting. One is the combiner function. This is an optional function you can specify, but it's very useful, especially if your reduce function has a nice mathematical property, if it's commutative and associative. That just means the order in which you combine things doesn't matter, like 1 + 2 = 2 + 1, and you can group the combinations differently. 1 + 2 + 3 was 1 + 2 + 3. Addition, like in our word count example, is a perfect case for this.
Okay, so if your reducer has that property, what does the combiner do, and why is it important for efficiency?
The combiner function actually runs on each map worker before the intermediate data is sent over the network during the shuffle phase to the reduce workers. It performs a partial merging or pre-aggregation of the data locally right there on the map machine. So back to our word count example. A single map task might process a document where the word "the" appears, say, hundreds of times. Instead of emitting "the" hundreds of times and sending all those separate tiny pairs over the network.
Which is a lot of network traffic.
Exactly. A combiner function, which is often just identical to your reduce function but running locally, would sum those up right there on the map worker's machine. It would then maybe just send a single pair, the 500, over the network, representing all those hundreds of ones combined into one partial count. This can drastically save network bandwidth. It's like doing a pre-sum locally before sending the numbers across the cluster. This is particularly effective when the same intermediate key appears many, many times within the output of a single map task, allowing for significant data reduction before that costly network shuffle.
That makes a lot of sense, especially for things like word count. And what about controlling where data ends up after the reduce step? Can users influence how keys are grouped for the final output files?
Yes, that's where custom partitioning comes in. By default, MapReduce uses a standard partitioning function, usually based on hashing the intermediate key, like hashkey mod r, to distribute the keys evenly across the R-reduced tasks. The goal is usually to balance the workload so each reducer gets roughly the same amount of data. But sometimes users have specific requirements for how their output should be organized. They can provide their own custom partitioning function. For example, suppose your intermediate keys are URLs and you want all data related to a specific hostname, like all URLs from google.com, to end up in the same single output file, regardless of the rest of the URL path. You could write a custom partition function that extracts the hostname from the URL key and then hashes only the hostname part to decide which reducer it goes to. For example, hash hostname key mod r. This ensures all related data for that hostname goes to the same reducer and thus ends up co-located in the same final output file. This gives you fine-grained control over the structure of your output, which can be crucial for subsequent processing steps or analysis.
Okay, we've gone through the elegant theory, the MapReduce model, and the really clever engineering behind the implementation, the fault tolerance, the optimizations like locality and backup tasks. Now let's see how this actually played out in the real world at Google. This is where it was put to the test on just an unimaginable scale. What kind of impact did MapReduce have internally when they rolled it out?
Well, the first version, as the paper mentions, was written in February 2003. They added significant enhancements like that crucial locality optimization later that year in August. And what they found pretty quickly was astonishing. It was broadly applicable to a huge range of problems, far beyond maybe just the initial indexing task they might have first envisioned it for. It wasn't just for one thing, it turned out to be a general-purpose big data processing tool.
What were some of these diverse use cases at Google where MapReduce quickly became indispensable? It sounds like it spread like wildfire.
It really did. MapReduce quickly became essential for critical internal tasks right across Google services. This included things like large-scale machine learning problems, training sophisticated models for ad ranking, spam detection, language translation requires processing vast amounts of data, and MapReduce was perfect for that. It was used for clustering problems, grouping similar items together for products like Google News and Frugal, which was their old shopping search engine. It was vital for extracting the data used to produce reports on popular queries like the Google Zeitgeist reports they used to publish, showing trending searches. It also handled extracting specific properties from web pages, maybe identifying geographical locations mentioned on pages to improve localized search results. And of course, it powered complex, large-scale graph computations like analyzing that massive link structure of the web graph to understand relationships and authority, feeding into things like PageRank. Its versatility was truly remarkable. Almost any large data transformation seemed expressible within its framework.
That kind of rapid, diverse adoption speaks volumes, doesn't it?
Yeah.
Especially at a company like Google, packed with brilliant engineers. What made it so successful for the individual programmers there? What problem did it solve specifically for them?
I think the key reason was its simplicity and accessibility. Before MapReduce, like we discussed, getting a distributed computation running efficiently and reliably on thousands of machines was a task for a small cadre of highly specialized experts in distributed systems. It was a lengthy, error-prone, incredibly frustrating process, but MapReduce made it possible to write a simple program and run it efficiently on 1,000 machines in the course of half an hour. Just think about that speed. From concept to massively parallel execution in 30 minutes.
That's game-changing for development speed.
Totally. It dramatically sped up the development and prototyping cycle. Engineers could iterate much faster, test ideas quickly on real-world scale data, and bring new features and products to market far more rapidly. And crucially, it allows programmers who have no experience with distributed and/or parallel systems to exploit large amounts of resources easily. This was a huge democratizer of computing power. It empowered a much broader range of developers to tackle these massive data problems without needing to become distributed systems gurus themselves.
Yeah.
It lowered the barrier to entry dramatically.
The numbers really back this up, don't they? The paper gives a snapshot of MapReduce usage at Google just a little over a year after its first version was created. What did that look like?
They do, and the numbers are staggering. In just 1 month, August 2004, looking at a subset of MapReduce jobs run at Google, they showed almost 30,000 jobs executed, 29,423 to be precise, each of those potentially involving thousands of machines. These jobs processed an astounding amount of data, over 3,288 terabytes of input data rate. That's over 3.2 petabytes. Just try to visualize 3,200 standard hard drives worth of information being processed in a month. And these jobs produced 193 terabytes of output data.
Wow, and the compute power.
The sheer scale of computation was mind-boggling. It used 79,186 machine days. That's equivalent to over 216 years of a single machine's compute time, all condensed into that single month through massive parallelism. And critically, underscoring the fault tolerance point. The average job experienced 1.2 worker deaths. This wasn't a theoretical issue, machines failed constantly, but the system kept running and completing jobs anyway, showing how integral fault tolerance was. Finally, they saw hundreds of unique map and reduce implementations developed internally, demonstrating its versatility and how broadly it was being applied across many different types of problems.
That's incredible scale and resilience. Perhaps one of the most compelling testaments to MapReduce's power, though, was its role in completely rewriting Google's production indexing system, the very heart of web search. That sounds like the ultimate stress test for any new technology, right? Rewriting the crown jewels.
Absolutely. The indexing system, as mentioned in the paper, takes over 20 terabytes of raw documents as input. Think 20,000 laptop hard drives worth of web pages. It processes this through a sequence of maybe 5 to 10 MapReduce operations, chaining them together, one feeding into the next. And the benefits of using MapReduce for this absolutely critical core system were profound. First, the indexing code became simpler, smaller, and easier to understand. All those gnarly complexities of fault tolerance, data distribution, parallelization were just hidden away inside the MapReduce library. They give an example. For one phase of the indexing computation, the C++ code dropped from approximately 3,800 lines down to about 700 lines.
That's a huge reduction, over 80% smaller.
Massive. Think about the reduction in complexity, the ease of maintenance, the fewer bugs. Just a huge burden lifted from the engineers maintaining that critical system.
What other benefits did it bring to such a vital system, beyond just smaller code?
It also led to increased flexibility. Because the performance of MapReduce was so good and the programming model was so clean, engineers could keep conceptually unrelated computations separate. They didn't have to tangle different kinds of logic together into one giant monolithic piece of code just to avoid making extra passes over the data, which was a common practice before. This separation made changing the indexing process incredibly easy. The paper states that a change that might have taken months to implement and carefully test in the old, complex, hand-coded distributed system could now often be done in just a few days in the new MapReduce-based system. Imagine the speed of innovation that enabled for search quality.
Wow, months to days.
And finally, the system became much easier to operate. Those constant headaches of machine failures, slow machines, network hiccups that were dealt with automatically by the library, it required significantly less human intervention, less firefighting. Plus, performance could often be improved relatively easily just by adding more machines to the cluster, a simple scale-out approach, rather than complex scale-up engineering on individual machines.
And in terms of raw performance, these MapReduce systems were blazing fast for their time, weren't they? What did the benchmark show for typical large-scale tasks?
Yeah, they ran specific tests to quantify MapReduce's efficiency on common large-scale tasks. For a grep example, just scanning 1 terabyte of data looking for a specific pattern, it took only about 150 seconds. That's roughly 2.5 minutes to scan a terabyte. The system peaked at an incredible data scan rate of over 30 gigabytes per second across nearly 1,800 worker machines, like reading 30 standard movies every second.
Incredible throughput.
Then sorting.
Sorting big data is always a classic benchmark.
For sorting 1 terabyte of data took 891 seconds, which is just under 15 minutes. What's impressive is that this time was actually comparable to dedicated, highly optimized sorting benchmarks that were specifically designed just for sorting, often running on specialized hardware. It showed MapReduce could perform at a competitive level, even for these specialized tasks, despite being a general-purpose framework with fault tolerance overhead. And we saw how critical backup tasks were here for sorting. Remember, without them, that same sort took 44% longer. And for demonstrating fault tolerance in practice during a sort, they intentionally killed 200 worker machines mid-operation. The system just recovered, rescheduled the work, and completed the sort successfully in just 5% more time than the normal, uninterrupted run. That's a profound testament to its incredible resilience and the effectiveness of those underlying mechanisms like task re-execution and backup tasks. #outro.
So when you pull it all together, what does this all mean for us? MapReduce, in essence, it provided this remarkably simple yet incredibly powerful way for programmers to process truly vast data sets. It really democratized large-scale distributed computing, didn't it? Making it accessible to a much broader audience of developers who, before, would have needed deep, specialized expertise in complex distributed systems. It was a real turning point in how we approach big data.
Absolutely. And from this deep dive, several key learnings really stand out, and they're still profoundly relevant in distributed systems design today. First, that by restricting the programming model, by forcing things into these core map and reduce functions, you can actually automate incredibly complex underlying mechanisms like parallelization, data distribution, and most importantly, fault tolerance. That power of abstraction was revolutionary.
Less is more, in a way.
Exactly. Second, network bandwidth is always a precious resource, especially in large clusters. Optimizing for data locality, like reading input data directly from local disks whenever possible, as MapReduce did, makes a massive difference in performance. Keep data movement minimal where it's most expensive. And finally, redundant execution through mechanisms like backup tasks for stragglers and just automatically re-executing failed map tasks is a remarkably effective, and sometimes maybe overlooked, way to mitigate the impact of slow machines and unpredictable failures. It ensures that even in imperfect real-world conditions, jobs can complete quickly and reliably.
It really makes you think, doesn't it? These core ideas of map and reduce, derived from fairly academic functional programming concepts, provided this simple language to express incredibly complex data transformations. And then the robust, intelligent implementation underneath made it all run reliably at scales previously unimaginable, turning what was a specialist nightmare into a common, accessible tool. MapReduce really laid the groundwork for so many of the big data systems we rely on today, things like Hadoop, Spark. It shaped an entire industry. It leaves you wondering, what other complex problems out there might be simplified if we could just find their underlying map and reduce operations, their core parallelizable patterns, and then build systems to handle all the messy details automatically.